lived. After 3 billion years of life, it was amongst the first creatures which would be visible to the naked eye. Both snowball events seem to have been crucial for evolution. The second could not have happened without the first, which saw the rise of organisms like this eukaryote. Although still tiny, it was 1,000 times larger than the early microbes. The mystery yet to be solved was how the ice melted. Once a planet like the Earth was frozen, it would reflect sunlight back into space and so remain frozen. What did happen to melt the ice? A hint can be found in this mine, in the Kalahari region of South Africa. This is the largest deposit of manganese to be found anywhere in the world. All the ore was laid down on the bottom of an ocean floor just when the first snowball event ended. Dr. Joseph Kirschvink from Caltech, who first published the Snowball Earth hypothesis, wondered if this deposit was in some way connected to the melting of the ice.
Good solid samples. I think maybe we could orient that one.
All the manganese in this mine were of manganese dioxide, which can only form with oxygen.
Only molecular oxygen, free molecular oxygen like we have in the air, is able to oxidize the manganese and make it fall out as this black rust. And what we're standing on today and what you can see here is the evidence of a massive amount of oxygen being put into the environment just at this time, just after the snowball.
He believes that the oxygen in the atmosphere of the early Earth was almost non-existent. After the first snowball event, it increased to around 1%. After the second event, it rose to 20%, close to the level in the atmosphere today. Oxygen molecules also produce an enormous amount of energy. And because energy became available, life was able to evolve into larger and more complex forms. Yet the questions kept coming.
It occurred to me that a frozen surface would not influence the working of geology. And it just hit me one morning that, oh, of course, the carbon dioxide from volcanoes would continue to build up in the air.
Volcanic gases contain large amounts of carbon dioxide, which normally dissolves into the seawater. But since the world was covered by ice, the carbon dioxide had nowhere to go but up. It continued to build to levels which may have been 2,000 times higher than those of today. As the Earth warmed, the ice began to melt.
You go from an average temperature of going down to -50, almost to +50. And at that point, you melt the ice extremely rapidly.
It was the Earth's own forces which brought the snowballs to an abrupt and dramatic finish. One study has suggested that when the surface of the sea reaches 45 degrees Celsius, about 110 Fahrenheit, it would trigger weather patterns that the world has never seen before or since. Temperature differentials would cause massive hurricanes to build. These hyper-hurricanes would generate waves the height of buildings. All this activity boosts oxygen production. Normally, nutrients which vent into the oceans from the Earth would settle back to the bottom or be consumed by bacterial life. In deep water, microbes aren't harmed by a surging ocean from the hyper-hurricanes. Many are transported from the depths to shallow waters. Then, when the winds died and the ocean calmed, the sun would heat the shallows. With sunlight and nutrients, photosynthetic microbes would explode in numbers, releasing yet more oxygen. The algal bloom would be so great that the seas would turn green. More and yet more oxygen would be pumped into the environment. The strength of life, which had survived 2 Snowball Earth periods, had changed the planet and was about to embark on a new chapter, but this time with abundant oxygen. Oxygen was the molecule that would change the world.
If Earth had never experienced these glaciations, life could have been quite different. Life on Earth might still be limited to the bacterial grade. We could still be just a planet of slimy oceans and stromatolites with nothing big enough to move and do things.
And oxygen allowed one more innovation without which larger animals could not exist. That was collagen, the scaffold which cells use to bind together. In this experiment in Japan, synthetic collagen is mixed with cells in a culture. These cells with collagen on the left of the screen multiply vigorously, while those on the right are static.